This is lab 4, magnetic field of a bar magnet. So the purpose of this lab was to prove that the magnetic field of a dipole on axis is inversely proportional to 1 over r cubed, to find the magnetic dipole moment of the bar magnet, and to use GlowScript to model magnetic fields of a dipole at different locations and compare our experimental results. And our overall results were that we can prove that the dipole on axis is inversely proportional to 1 over r cubed, that the magnetic dipole moment was 3.788418 amps per meter squared, and that when we compared the experimental value to the GlowScript value for 45 degrees magnetic field, there's a 182.112% difference. So the first main concept of this lab is the Biot-Savart law for dipoles on axis perpendicular. And they're pretty similar equations, other than that if it's on axis, there's an extra scaling factor of 2, and that the directions are opposite. We also have the distance dependence of magnetic dipoles, which shows that you can prove that magnetic dipole is equal to k r to the n, where k is a combination of constants and n is a distance dependence on magnetic fields from a dipole. And this equation can be plotted linearly to find the value of n and k. Another concept is the general Biot-Savart law equation, which we don't really use in class, but it's useful for like GlowScript to find magnetic fields from a dipole when it's not on axis or perpendicular. So the procedure of this lab was to first find the magnetic north by finding when b of x equals 0, then to locate the magnetometer on the phone. And then using this, we would find when b of x equals 20, 70, 120, 170, and 220 when the magnetometer is on the axis. We'd record these distances and repeat each distance 2 more times. And then we record the value of slope and the y-intercept from that linear equation on the spreadsheet. And as you see from the picture on the right, the system is the magnetometer and magnet, and everything else is the surroundings. The second part of the lab was the perpendicular 45-degree section, where we first found the distance when the net magnetic field is 100, record this distance in by, and we move up the phone up the same distance, so it creates this 45 degrees. And we recorded bx, by, bz. We did this 2 more times, and then we adjusted by to account for the Earth's magnetic field, and we recorded the average distance in net magnetic field. So here are the results. The left side doesn't really matter as much, it's more the graph on the right, and as you can see, you have y equals negative 2.9593x minus 14.093. And based off this equation, we can see that n is equal to negative 2.9593, which basically means r to n becomes 1 over r cubed, which shows that a dipole on axis inversely proportional to 1 over r cubed, and ln of k would equal negative 14.093. And for the 45 degrees part, the average distance was 0.2093 meters, and the average net magnetic field was 0.00493441 teslas. So some observations from the lab is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field. That's because as it gets so far away, r becomes so large that magnetic field becomes near zero. And as it becomes magnetometer moves closer, the x component becomes larger because 1 over r cubed becomes larger, so the magnetic field increases. And here are the calculations for this lab. So as you can see, we've showed that n equals approximately negative 3, and that since ln of k is negative 14.093, by manipulating this value and comparing it to the dipole on axis equation, you can get that the dipole moment is equal to 3.788418 per meter squared. And for the GlowScript code, we first create constants, magnet, and the magnitude of magnetic moment. And we create the magnetic dipole field function on this page. And then we create the observation locations for on-axis perpendicular, and then we create arrows to reflect the direction and magnitude of the magnetic fields. And then we printed the magnetic field vectors at each location. And for the 45 degrees part, we used the dperp from the experiment to create an arrow, and this arrow will reflect the magnitude and direction, and printed the vector and magnitude of magnetic field. So here are the results. As you can see, the directions and magnitude of magnetic field are expected, they're opposite, and that the magnitude on axis is double that of the perpendicular, which shows that the 2 scaling factor. And when we compare the 45 degrees off-axis value from the experiment and the model, from the experiment is 0.000493441 teslas, as said before, but from the model is 0.000230998 teslas, which is 182.112% difference, which is very large. But this is because of some sources of error, such as unknown sources of magnetic field. The magnetometer on the phone was not completely accurate, possibly. The placement of the phone could have been inconsistent, so some human error. And there could have been measurement error when finding distance from magnet to magnetometer. So for like the 45 degrees axis portion, distance could have been inconsistent when we moved it up compared to left and right. So overall, what if you hadn't oriented your experiment to compensate for magnetic north? The x component would change because the magnetic field of Earth would contribute to bx, which would change results in spreadsheet, and the y component would change because the magnetic field of Earth would contribute differently to by. And if we stuck two identical magnets together, what would happen? The magnitude of the magnetic field would increase due to having two magnets instead of one, and the distance for each value of Bx would increase because the magnetic field is stronger. So overall, the magnetic field of dipoles are inversely proportional to distance slash 1 over r cubed. Magnetic dipole moment of the bar magnet was 3.788418. And as the magnet gets closer to the observation location, the magnetic field increases. And it was not very accurate, the experiment, because of many sources of error.